Your mission, should you decide to accept it, is to learn about energy. Chapter 9, Energy. Energy can change from one form to another without a net loss or gain. So we're going to talk about that today in here. And while energy is a pretty common concept in science, it's one that's pretty hard to observe. You can't just, if I said, hey, go look at some energy, what would you be looking at? What we see is when energy changes. So we can say we've got wind energy, we're changing into electricity, we kind of notice those things. But we're usually looking for when it's transformed more than anything else. Well, let's start back at the beginning. Let's start with work. Okay, so work is, when we're talking about work, we're talking about a force or a net force that moves an object in a direction. And when we talk about work, we say that work is force times distance. Okay, so we do work if we lift something up. The heavier it is, the more work we have to do, or the higher we lift it, the more work we do. Any of those. So anytime that we have force times distance, that's going to be our work. So here's a good formula, one that you'll need to remember, because we're going to use that over and over. Work equals force times distance. Okay, so if we were talking about lifting a load, if I lift two loads or twice that much in that same distance, then I've done twice as much work. Or if I lift that same load, but I do it twice as far, I've done twice as much work. So here's our weightlifter. He's lifting the barbell. He's done a lot of work to lift that. It's pretty heavy. If he were to lift more, he would do more work. Or if he were to lift higher, he would do more work. But if he's just holding it over his head, once he gets it up there and he's holding it, there is no work being done when it's just up there. Despite the fact that he might be getting heavy, it's going to be hard for him to do. He's not doing any work. Now, the barbell might be trying to do some work on him, but he's not doing anything as long as it's not moving. Same thing, we get work done. Like if an archer pulls back on a bowstring, we're doing work on the bow. We're pulling against the elastic force of the bowl. Or they talk about a pile driver, a big weight that if you lift it, you're doing work against the force of gravity. Or anytime that you do push-ups, you're doing work against your own weight, compared to gravity. So if you slow down a car, anytime you're changing the speed of an object, you're going to be doing work. So if you step on the brake, slow down a car, that's going to be doing work. Work involves transferring energy between something and its surroundings. So whether we're speeding something up, slowing something down, any of those would be examples of work. And when we do work, remember we said that work was force times distance. Force, our label is in newtons. Distance is in meters. So work's label is Newton meter or a joule, J. So if you're going to do bigger amounts, you got kilojoules, you got megajoules, and so on. So in other words, it says to stop a truck at 100 kilometers per hour would take megajoules of work, so quite a bit more in that example. All right, so let's say that you wanted to, what are we doing here? Apply a 60 Newton force to 32 kilogram package, push it 4 meters across the mailroom floor. How much work did you do? So here's the key to that. Remember, work is force times distance. Force, 60 newtons. Distance was 4 meters. There's no mass involved here. We don't really care about the mass of this object. So the actual work done is going to be 240 joules in that example. All right, power. If we're talking about power, we're talking about how much work we do in the amount of time. So power is work divided by time. And it's rate. So basically we're talking about work. We might, we both might do the same amount of work, but if one of us does it faster than the other one, we have more power. So if we're talking about a high power engine, it's an engine that maybe delivers twice the power of another one, but it doesn't necessarily mean it's going to go twice as fast. It might just be moving twice as much mass. or twice the power means it could do twice as fast, could be twice as fast, or it could be kind of a combination of both things. So when we're talking about power, we're just talking about how much work we can do in the amount of time. And we usually do that in terms of watts. So if we do 1 joule of energy in 1 second, we have 1 watt. So think about this. You have 60 watt light bulbs, and that's a pretty common light bulb. It means it's doing 60 joules of work every second to keep that thing lit. If we need bigger ones, we go kilowatts, megawatts. If we need to go back to the future, we do 1.21 gigawatts. So then we'd have to have a lot of energy, a lot of power. Here's the space shuttle. It only does 33,000 megawatts of power when it lifts off. So, it says it's burning fuel at the rate of 3,400 kilograms per second. So think about that. We went and watched that last year. It's taking 3,400 kilograms of fuel. That's probably close to 7,000 pounds of fuel that it burns per second as it launches. Usually, if we're talking in the U.S., we usually talk about horsepower. We're talking about engines and kilowatts. If we're talking about electricity, but they're both the same. They are related. They're same. They both are meaning the same type of thing. So we could say horsepower. It's the same as 0.75 kilowatts. So if you have a 134 horsepower engine, it's also be a 100 kilowatt engine. It's just our convention has always been to talk about horsepower. All right, if a forklift is replaced with a new forklift that has twice the power, how much greater load can it lift in the same amount of time? If it lifts the same load, how much faster can it operate? All right, so think about those. Well, it delivers twice the power. If it delivers twice the power, it will lift twice the load in the same amount of time. So you lift twice as much, apply twice as much force. Or the same load in half time, whichever way you want to look at it. All right, 9.3, mechanical energy. 2 forms of mechanical energy that we're going to talk about are kinetic and potential energy. We're going to get into this. If an archer pulls back a bowstring, we've put it's taken a force to do that. That bow has now gained some energy. It's got the ability to do work. If you let go of it, it's now going to shoot the arrow, and that's going to get that's going to give a lot of energy to that arrow. So we have done some work on that bow. We've applied some energy to it. Work's also done if you raise the pile driver, this heavy weight. That's done a lot of work. Or if we're talking about a spring. If I've done something to the spring, I maybe wind the spring, or I've stretched the spring. Those are also mechanical. We've done some mechanical energy in those cases, and they might be used to run a clock or a bell, or sound alarm or something like that. So, if something's been acquired that enables the object to do work, this may be just in terms of atoms. We might have been compressing atoms or separating physical, attracting bodies. So, for instance, think about pulling a magnet apart, or we could be rearranging molecules, electric charges, and so on. All of those are examples, of things that maybe you don't think of as work, but they would be work if we're looking at them, in that subatomic level a lot of times. Okay, so the property of an object or system that enables it to do work is energy. So this is a good definition. We're talking about energy. Energy is the ability to do work. And we usually measure energy in joules. Mechanical energy is usually, has to do with the position or moving of something. And so that's pretty common energy that we talk about, that we see every day. So if I move something, I lift something up, that's examples of mechanical energy in that case.